This lecture is a continuation of the previous lectures on black holes, and the focus for this lecture will be on gravitational collapse. The most simple black hole is given by the Schwarzschild solution, which describes a static, spherically symmetric black hole. Using the Curvature coordinates that I introduced in the last lecture, we can write the metric as ds squared equals minus 1 minus 2m over r dt squared plus 4m over r dt dr plus 1 plus 2m over r dr squared plus r squared d omega squared, where d omega squared is shorthand notation for d theta squared plus sine squared theta d phi squared. Now in these coordinates, these Schwarzschild coordinates, r is the areal radius, r equal 2m is the horizon of the black hole, and r equals 0 is the black hole singularity. We can plot the horizon and the singularity on a TR diagram. So let me bring this plot in from the last lecture. This is a plot of the TR plane. So this is the horizontal axis is the areal radius, and the vertical axis here is the t coordinate. The heavy black line is the horizon at 2m. And the singularity is at r equals 0, so I'm going to put a little squiggly line to remind ourselves that the curvature is infinite along r equals 0. Now keep in mind each point in this diagram is a two-dimensional sphere with areal radius r, and the curves here show the directions for null rays, the null geodesics in the RT plane. And you'll notice that inside the black hole, in this region where r is less than 2m, less than the horizon size, that all of these null rays are directed in towards the singularity. And since nothing can travel faster than the speed of light, any observer or particle that passes, say, this event right here, must stay within the future light cone, which is tipped towards the singularity. So this observer or particle is destined to hit the singularity somewhere in this region. Now in earlier lectures we used the Schwarzschild metric to describe the geometry outside a static spherical body of mass m. For example, our sun is approximately static and spherically symmetric, so this metric describes the geometry in space-time outside the sun. On a diagram like this, the surface of the sun would be, say, right here. So this is the radius of the sun, which is approximately 700,000 kilometers. So this metric applies to the region outside the surface of the sun, and inside the surface of the sun the metric is something else that depends on the details of the matter that the sun is made from. So for the sun we need to throw away this part of the diagram to the left of this heavy black line and replace it with something else. Now you might wonder how I know to draw the surface of the sun out here outside the horizon and not inside the horizon. And that's because if we compute 2m, where m is the mass of the sun, we obtain approximately 1.5 kilometers, much less than the actual radius of the sun. So the radius of the sun would have to be less than 1.5 kilometers in order for the surface of the sun to be inside the horizon. But what would happen if the sun began to collapse? So the surface of the sun, instead of following a world line of constant areal radius like this, the surface of the sun follows a world line like this with a decreasing areal radius. Well, the first thing that you might wonder is, can we still assume that the geometry outside the surface of the Sun is described by the Schwarzschild geometry. For example, you could imagine this collapsing body produces some sort of perturbation on the gravitational field that propagates outward into the exterior region and alters the exterior geometry so it's no longer exactly given by the Schwarzschild metric. But that actually doesn't happen. When a body collapses like this, the exterior region remains Schwarzschild, and what happens is the body simply uncovers more and more of that Schwarzschild geometry as it collapses. In fact, the body can collapse clear through the horizon, and at that point the body becomes a black hole. So how do we know that the geometry outside a spherical collapsing body is given by the Schwarzschild geometry? Well, the answer is contained in what's called Birkhoff's theorem. Birkhoff's theorem tells us that the most general spherically symmetric vacuum solution of Einstein equations is the Schwarzschild solution. A couple of lectures ago, I derived the Schwarzschild solution by assuming the spacetime was vacuum, spherically symmetric, and static. And what Birkhoff's theorem shows is that we really didn't even need to assume that the spacetime was static. All we needed to assume was that it was spherically symmetric and vacuum. So when a body collapses, as long as it's spherically symmetric, then the only possible exterior solution, where the region where there's vacuum, is the Schwarzschild solution. And as the body collapses, it uncovers more and more of the Schwarzschild geometry. Let's take a few minutes to recall the life cycle of a star. So a typical star is made mostly of hydrogen. And the star will burn hydrogen. It will fuse together 4 hydrogen atoms to create a helium nucleus, and in the process release energy. And this energy supplies the thermal pressure that holds the star up and prevents it from collapsing under its own weight, under its own gravitational pull. Now, when the hydrogen is gone, the star can begin to fuse the helium nuclei together to form heavier elements. And this process can continue all the way up to iron. You'll recall iron has the largest binding energy per nucleon of any element, so it's not possible to fuse together iron atoms and have a release of energy. So as the star continues this fusion process in its outer layers, a core of iron builds up on the inside, and that iron core continues to grow until it doesn't have enough thermal support to keep it from collapsing. Now the details of what happens depend most crucially on the mass of the star. So if the star is small, so a mass less than about the mass of the Sun, then the end product is what's called a white dwarf. Now a white dwarf is supported from further gravitational collapse by electron degeneracy pressure. Electron degeneracy pressure is a result of the Pauli exclusion principle, which tells us that electrons can't occupy the same state. And this effectively limits the physical space occupied by the material in the star and provides the pressure to support the star from further collapse. The typical mass of a white dwarf star is about 1 times the mass of the Sun, and typical radius of the surface is about 1,000 kilometers. So this is still well below 2m. So 2m for a white dwarf would be about 1.5 kilometers. This would be the horizon of a black hole of the same mass. Now, if the star has a mass greater than the mass of the Sun, then electron degeneracy pressure isn't strong enough to prevent it from further collapse. So if we have a medium-sized star, so we'll take the medium-sized star to have a mass around 1 or 2 solar masses. The end result is a neutron star. Now, in a neutron star, the electrons and protons have been forced together through inverse beta decay to form neutrons. So a neutron star is basically a big ball of neutrons, and it's supported from further collapse by neutron degeneracy pressure. So like electron degeneracy pressure, this comes from the Pauli exclusion principle and effectively limits the physical space occupied by the neutrons. Now, a typical size for a neutron star would be about 10 kilometers. And this is larger than the value of 2m, which would be about 2 or 3 kilometers, a few kilometers. Now, if the mass of the star is greater than about 2 times the mass of the Sun, neutron degeneracy pressure isn't strong enough to prevent the star from further collapse. So for a large star, which we'll take to be roughly 2 solar masses or more, then the end result, we believe, is a black hole. Or said a little more precisely, when the mass is greater than about 2 times the mass of the Sun, there's no known physical mechanism that can prevent the star from collapsing to a black hole. And of course, there are lots of stars in the universe with masses greater than 2 times the mass of the Sun, in some cases much greater than twice the mass of the Sun. And those stars eventually run out of nuclear fuel, so this process of collapse to forming a black hole is really quite common. So what does the collapse look like on a Schwarzschild diagram? So here's the areal radius r, here's the Schwarzschild time coordinate t, and this is the Schwarzschild geometry. Every point in this diagram is a two-dimensional sphere. Now let me draw the surface of the star. So let's begin here. The star begins to collapse. This is the singularity, squiggle line here. And of course, 2m is the event horizon. Now, the interior of the star is this region in here, and we're discarding the Schwarzschild geometry in here because the geometry is something else, depends on the details of the matter. So even though we don't know what the geometry is in here, we do know what the geometry is out here. It's the Schwarzschild geometry. So in particular, the surface, once it crosses the horizon, it has no choice but to run into the singularity. In fact, if you like, you can think of a particle that's riding along the surface. That particle must always move within the forward light cone. And the forward light cone's here are tipped towards the singularity. So that particle riding along the surface has no choice but to hit the singularity, and it can never escape to the exterior region. So you see from this diagram that once the surface of the star crosses its own event horizon, then nothing can prevent it from full collapse to a singularity. What I'd like to do next is spend a little bit of time talking about a model for the interior geometry, for the solution in the interior of the star. Now, the Einstein equations are much too complicated to solve analytically for any realistic model of the star's interior. So this model I'm about to show you is a highly idealized model. We'll not only assume that the star is spherically symmetric, but also assume that the material is simple pressureless dust. So we'll assume that the stress energy momentum tensor is the mass density rho times u mu u nu, where u is the phore velocity of the dust. So we can imagine that at earlier times, prior to this t=0 surface, the star had some pressure that supported it from collapse. Then at t=0, the pressure support was lost and the star begins to collapse. And we model the material in the star beyond t=0 as a simple dust. And it's this region of the space-time that I want to describe. So I'll first write down the interior solution, and we'll verify that it satisfies the matter equations of motion and the Einstein equations. And then we'll worry about how that interior solution is joined together along the surface of the star with the exterior solution, which is Schwarzschild. So this will be the solution for a collapsing ball of dust. So we'll assume the ball is spherically symmetric. And dust means the stress energy momentum tensor is given by the mass density times the phore velocity u mu u nu. I'll draw a picture of the collapsing ball as a wedge. Every point in this wedge is a two-dimensional sphere. This is the same wedge as we showed in this diagram. And I'm going to use coordinates to describe the geometry in here, which I'm going to call chi and eta. So we can think of chi as a radial coordinate, so it monotonically increases as the areal radius increases, starting with chi=0 out to the surface of the star. And eta we can think of as a time coordinate. It starts at 0 at the moment the star begins to collapse, and it has some maximum value before the singularity forms. Here's the singularity. And the maximum value of eta is actually pi. And the maximum value of chi, the value of chi that corresponds to the surface of the star, is sine inverse, or arc sine, of the square root of 2m over some constant r0. And now let me draw a few of the coordinate lines. So these lines are lines of constant chi. And the surface of the star itself is a surface of constant chi with the value given by sine inverse of square root 2m over r0. And the surfaces of constant eta, this is eta=0, and those surfaces look something like this. So the coordinates are eta, chi, theta, and phi. Remember, each point in this diagram is a two-dimensional sphere with coordinates theta and phi. So the metric for this collapsing ball of dust is ds squared equals r0 cubed divided by 2m times cosine to the fourth power of eta over 2 times the quantity minus d eta squared plus d chi squared plus sine squared chi d omega squared. And the density of the dust is equal to 6m divided by 8 pi r naught cubed times cosine to the minus 6th power of eta over 2. And the forward velocity of the dust is given by the zero component, or the eta component, is square root of 2m over r naught cubed times cosine to the minus 2 power of eta over 2, and the other components are 0. So you can see from this form of the forward velocity that the dust particles travel along these chi equal constant coordinate lines. So the dust just travels along these lines. So these are the dust world lines. And they all converge here at the tip of the wedge. And you can see here, when eta is equal to pi, the density goes to infinity. So this would be the cosine of pi over 2 is 0. 0 to the minus 6 power is infinite. Now we still need to verify that this metric, density, and forward velocity satisfy the equations of motion. So first let's look at the dust equations. If we remember, for any perfect fluid, the equations of motion are just the equations of local energy momentum conservation. So for the case of dust, T mu nu is rho u mu u nu. We can write this out in detail as partial mu of rho u mu u nu plus gamma mu mu sigma rho u sigma u nu plus gamma nu mu sigma rho u mu u sigma. And now if we remember that only the eta component of u is non-zero, this becomes partial with respect to eta of rho u eta u nu. So the free index is nu here, plus gamma mu mu eta rho u eta u nu plus gamma nu eta eta rho u eta u eta. Now if we examine these Christoffel symbols, we have a sum over mu. So this includes things like gamma eta eta, and it turns out also gamma chi chi eta. It turns out that all of these are equal to one another. So gamma theta theta eta equals gamma phi phi eta. These are all equal to minus tangent of eta over 2. And for these Christoffel symbols, we already know that gamma eta 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 is minus tangent eta over 2, but all the others vanish. So chi eta eta, gamma theta eta eta, gamma phi eta eta, these are all equal to 0. Now let's put all this together, and you'll notice that when the index nu is equal to chi, then this term is 0 because the chi component of u is 0. Here the chi component of u is 0, so this term is 0. And also this term is 0 because gamma chi eta eta is 0. And similarly, when the index nu is equal to theta or phi, we just get 0 equals 0 from this equation. So the only non-trivial case is when nu is equal to eta. And we obtain 0 equals partial eta of rho u eta squared plus gamma mu mu eta is the sum of all these Christoffel symbols, so that's minus 4 tangent of eta over 2 times rho u eta squared. And this term with nu equal to eta, gamma eta 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 is minus tangent of eta over 2 times these factors, rho u eta squared. This, of course, simplifies to partial eta of rho u eta squared minus 5 times tangent of eta over 2 times rho u eta squared. And now if we remind ourselves the form that rho and u eta take, they're written down right here. We find that rho u eta squared is equal to 3/2 m squared over pi times r naught to the 6th power times cosine to the minus 10th power of eta over 2. Now we can insert this into our equation, which becomes 0 equals partial eta of 3m squared over 2 pi r naught to the 6th power times cosine to the minus 10th power of eta over 2 minus 5 times tangent of eta over 2 times 3m squared over 2 pi r naught to the 6th times cosine to the minus 10th power of eta over 2. Of course, these factors, 3m squared divided by 2 pi r naught to the 6th, cancel in this equation, and we're just left with the derivative of cosine minus 10. So that would be minus 10 times cosine to the minus 11th power times the derivative of cosine, which is minus sine, and then we have another factor of 1/2 coming from the differentiation of eta over 2. And this term is minus 5 times, let's write tangent as sine over cosine, so this is sine of eta over 2 times cosine to the minus 11th power of eta over 2. And now you can see that these two terms cancel. We have 2 minus signs gives an overall plus sign, and 10 divided by 2 is 5. Here we have minus 5. And both of these terms have factors of sine eta over 2 and cosine to the minus 11th power of eta over 2. So we have now verified that the matter equations of motion hold for this solution. And now we need to verify that the Einstein equation holds. That's g mu nu, Einstein tensor, equals 8 pi times t mu nu. Now, when we compute the Einstein tensor for the metric that I gave, we find that the only non-zero components are when mu and nu are both equal to eta. And what we obtain then for g eta eta is 12m squared divided by r naught to the 6th power times cosine to the 10th power of eta over 2. For the stress energy momentum tensor, that's rho times u mu u nu, the only non-zero components are when mu and nu are both equal to eta. And then this is equal to rho times u eta squared, which you might recall is equal to 3m squared divided by 2 pi r naught to the 6th power times cosine to the minus 10th power of eta over 2. So you can see if we multiply this by 8 pi, and the pi's cancel, 8 times 3/2 is 12, and that's precisely what we have here, 12m squared over r naught to the 6th, and then cosine to the minus 10th power. So Einstein equations are satisfied. So we've now verified that this metric, density, and 4 velocity is a solution of the matter and Einstein equations of motion. And this solution describes a collapsing ball of dust. And by the way, this is referred to as the Oppenheimer-Snyder dust solution. Of course, this is just the interior solution. Outside this ball of dust, or this star, we have the Schwarzschild geometry. And we need to know that the interior solution and the exterior solution can be glued together in a continuous fashion. So in particular, we need to know that the geometry along the surface of the star, we need to know that that's the same geometry as viewed from the interior as it is as viewed from the exterior. So this is the surface of the star. And from the interior, it's given by the coordinate value chi equal to sine inverse of square root of 2m over r naught. So the three-dimensional geometry of this surface is obtained by inserting chi equal to this value into the line element here. So if we do that, then of course d chi squared vanishes, and sine squared of chi is just the square of square root of 2m over r naught. So that's 2m over r naught, which partially cancels these factors. And what we're left with then for the surface geometry this is as viewed from the interior of the star. Is just ds squared equals r naught cubed over 2m times cosine to the fourth power of eta over 2 times minus d eta squared plus r naught squared times cosine to the fourth power of eta over 2 times d omega squared. Now the exterior geometry that's just Schwarzschild, and remember we've been using Curvature coordinates, so the line element is minus 1 minus 2m over r dt squared plus 4m over r dt dr plus 1 plus 2m over r dr squared plus r squared d omega squared. Now the surface of the star as viewed from the outside, from the exterior, is some curve in the TR plane. So it's this curve, and we can parameterize the curve using the coordinate values eta. So each point along this curve has a value of eta that it inherits from the coordinates on the inside. So we'll describe the surface of this star from the outside as some parameterized curve T of eta, R of eta. Then the surface geometry as seen from the outside this is obtained by inserting t as a function of eta and r as a function of eta into this line element. And what we obtain then is ds squared equals minus 1 minus 2m over r, now that's r as a function of eta, times, and dt I'm going to write as t dot times d eta, and I'll put the d eta outside of all of these terms. So this is t dot squared plus 4m divided by r of eta times t dot r dot plus 1 plus 2m over r of eta times r dot squared, all of that times d eta squared. So that's all of these terms. Then of course we have r squared, that's r as a function of eta squared times d omega squared. So now we have the surface geometry as viewed from the interior and the surface geometry as viewed from the exterior, and of course these need to match. So these two line elements should be equal to one another. So we first equate the coefficients of d omega squared, and that tells us r as a function of eta. And then we equate the coefficients of d eta squared. So that gives us the following two results. We have r of eta equals capital R naught times cosine squared of eta over 2. And the other equation that comes from equating the coefficients of d eta squared is minus 1 minus 2m over r times t dot squared plus 4m over r t dot r dot plus 1 plus 2m over r times r dot squared equals minus r naught cubed over 2m times cosine to the fourth power of eta over 2. Now we can insert this result for r of eta everywhere we see r here, and also differentiate this with respect to eta and insert that for r dot here and here. Then solving this equation for t dot gives t dot equals m times sine of eta minus r naught times the square root of r naught over 2m minus 1 times cosine to the fourth power of eta over 2, all of that divided by 2m over r naught minus cosine squared of eta over 2. And now we can integrate this equation to obtain t as a function of eta, and the result is 1/2 square root of r naught over 2m minus 1 times the quantity r naught plus 4m times eta plus r naught times sine of eta plus 4m times the natural log of cosine of eta over 2 plus sine of eta over 2 divided by square root of r naught over 2m minus 1. So these calculations are straightforward in principle, but they're actually a bit trickier than you might suspect. It took me the better part of a day to obtain this answer in this nice, relatively simple form. And by the way, you'll notice I've chosen the integration constant here so that t is equal to 0 when eta is equal to 0. So these two equations define the surface of the star as viewed from the exterior Schwarzschild geometry, and by construction, the geometry of the surface matches precisely the geometry of the surface as viewed from the inside, from the interior dust solution. So the interior and exterior geometries match at the surface. And that means that we can connect the interior and exterior continuously. But that does not necessarily mean that the geometries connect smoothly. Let me give you a simple example to illustrate the issue here. We can take a cylinder So this is a cylinder. And we can put a top on it, a disk. So here we have a disk, a flat disk, and we have a cylinder, and they can be connected continuously. So they connect along the rim here, this circle. So the geometry of the circle is the same as viewed either from the disk or from the cylinder. So the connection is continuous, but in this case it's not smooth. So a continuous connection requires the geometries to match at the surface, and the geometries are intrinsic geometries. So we examined the intrinsic geometry of the three-dimensional surface from interior and exterior and made sure that those intrinsic geometries matched. To determine whether the matching is smooth, we have to examine the extrinsic geometry. Or the extrinsic curvature. I discussed briefly in some of the earlier lectures in this series the distinction between intrinsic and extrinsic geometries, or curvature. The intrinsic geometry always refers to the metric. It's what the metric defines. Extrinsic curvature always refers to the way that a surface is embedded in a higher dimensional space, or space-time. So the idea is that we have a surface, and this might be a one-dimensional surface in a two-dimensional space, like I've drawn here, or it might be a three-dimensional surface in a four-dimensional space or space-time. So in order to quantify the way this is bent or shaped with respect to the embedding space-time, is we examine the normal vectors. So these are unit normals. And to compare them, we parallel transport. For example, we'll take this normal vector and parallel transport it so that it sits at the same point as this vector. So here's the parallel transported version of this vector. And then we subtract. And the result is a vector that tells us how bent this surface is within the embedding space or space-time. So let's call these normal vectors n, components n mu. And let's also introduce a set of basis vectors in the surface. So here's a vector e with components e mu. So the way the extrinsic curvature is defined is by parallel transporting the normal, and that's done with the covariant derivative of n along the direction of some basis vector e. So this is what we'll define as the extrinsic curvature, and it's a vector for each basis vector. So in general, if we have several basis vectors, say if the surface is three-dimensional, then we'll have three basis vectors. We'll label them with a subscript I. And then the extrinsic curvature will be a set of vectors, k mu sub I. And these extrinsic curvature vectors tell us how the surface is curved or bent within the embedding space for each one of the basis vector directions. Now let's verify that the interior dust geometry connects smoothly to the exterior Schwarzschild geometry. So let me draw the wedge once again. Here's the singularity. This is the surface of the star. And we need to construct, at each point along the surface, we need to construct a unit normal in mu, and we need to construct a set of basis vectors in the surface. So here's one of those basis vectors. Let's call it E0. And there are two other basis vectors that are perpendicular to this diagram. Remember, each point in this diagram is a two-dimensional sphere. So we'll call these other basis vectors E2 and E3. So the set of basis vectors is E0, E2, and E3. And of course the normal vector is n. So we will use these vectors to construct the extrinsic curvature of the surface, but the extrinsic curvature will depend on whether this surface is viewed as a subspace of the interior geometry inside the dust or as a subspace of the exterior geometry, the Schwarzschild geometry. So we'll have to compute the extrinsic curvature for both cases and then show that they match. And then we'll know that the matching of the two geometries, inside and outside, is smooth. So let's begin by computing the extrinsic curvature of this surface as a subspace of the interior geometry. So the surface as subspace of the interior. Let's start by constructing this unit vector E0. This is easy. This is a unit vector along the surface of the dust in the plane perpendicular to the two spheres. So this is just the forward velocity of the dust at the surface. If you'll recall, that's equal to square root of 2m over r naught cubed times cosine to the minus 2 power of eta over 2. That's the eta component, and the other components are 0. And now we can construct the unit vector n. It's a vector that's perpendicular to this vector. It's in the plane orthogonal to the two spheres, so it only has components in the eta and chi slots, and it's normalized. So those conditions uniquely define this normal vector as 0, square root of 2m over r naught cubed times cosine minus 2 of eta over 2, 0, 0. And now the other two basis vectors are E2 is 0, 0, 1 over r naught cosine squared eta over 2, 0, and E3 is 0, 0, 0, 1 divided by r naught times cosine squared of eta over 2 times sine of theta. So you can verify that all of these vectors are normalized and they're all orthogonal to one another. And now we compute the extrinsic curvature, of course using the interior metric. So I'll remind you the metric inside the ball of dust is r naught cubed over 2m times cosine to the minus 4 to the plus 4 power eta over 2 times minus d eta squared plus d chi squared plus sine squared of chi d omega squared. And now the extrinsic curvature is defined as k mu sub I equals E nu I del nu in mu. And this is now a straightforward calculation using this metric and these basis vectors. And the result is the following. The zeroth extrinsic curvature vector is just 0. The second one, the extrinsic curvature vector associated with E2 is 0, 0, 1 over r naught squared times square root of 1 minus 2m over r naught times cosine to the minus 4th power of eta over 2, 0. And K3 is 0, 0, 0, 1 over r naught squared times square root of 1 minus 2m over r naught times cosine to the minus 4th power of eta over 2 times sine inverse, that's 1 over sine of theta. So this is the extrinsic curvature of the surface as a subspace of the interior geometry. And now we turn to computing the extrinsic curvature of the surface as a subspace of the exterior. Once again, we need to construct the basis vectors E0, E2, E3 that span the surface, and also the normal vector in mu. So we'll start with E0. Remember, this is just the forward velocity of the dust at the surface. Now the forward velocity is written as a derivative operator as 2m over r naught cubed times cosine to the minus 2 power of eta over 2 d by d eta. And we can use this to find the components of u in the coordinates used in the exterior in the following way. This is 2m over r naught cubed square root times cosine to the minus 2 power of eta over 2 times t dot d by dt plus r dot d by dr. And the dot here refers to differentiation with respect to eta. We wrote down t dot and r dot explicitly before, so this factor times t dot is the t component of u. This factor times r dot is the r component of u. In other words, those are the t and r components of our vector, our basis vector E0. So when we put all that together, we find that E0 has the first component, the t component, is 2m over r naught cubed times m times sine of eta minus r naught times the square root of r naught over 2m minus 1 times cosine to the 4th power of eta over 2. All of that divided by cosine squared of eta over 2 times 2m over r naught minus cosine squared of eta over 2. So that's the t component. The r component is minus square root of 2m over r naught times the tangent of eta over 2. And the theta and phi components are both 0. The next step is to construct the normal vector n. This vector lies in the plane that's orthogonal to the two spheres, so its theta and phi components of n are both 0. This vector is orthogonal to E0 and it's normalized, and that completely determines the vector to be the following. In mu is equal to 4m times the square root of 1 minus 2m over r0 minus the square root of 2m times r0 times the sine of eta, all of that divided by minus 4m plus 2r0 times cosine squared of eta over 2. That's the t component. The r component is square root of 1 minus 2m over r naught. And the theta and phi components are both 0. And now it's easy to construct the remaining two basis vectors. This is the basis vector that points along the d by d theta direction. It's 0, 0, 1 over r naught cosine squared of eta over 2, 0, and E3 is 0, 0, 0, 1 divided by r naught cosine squared of eta over 2 times sine of theta. And now we compute the extrinsic curvature, of course using the exterior metric, which is minus 1 minus 2m over r dt squared plus 4m over r dt dr plus 1 plus 2m over r dr squared plus r squared d omega squared. So the extrinsic curvature is k mu sub I equals ei nu del nu in mu. Now the only thing that's tricky about this calculation is here we have derivatives with respect to the coordinates t and r, but the components of the vector n are written in terms of this parameter eta rather than t and r. So when you differentiate n along the E0 direction, you need to use E0 nu partial nu n mu equals square root of 2m over r naught cubed times cosine to the minus 2 power of eta over 2 times d by d eta acting on the components n mu. This is just the vector E0 written as a derivative operator that's proportional to d by d eta. So with this hint, I'll leave it as an exercise for you to verify that the extrinsic geometry using these basis vectors and normal vectors turn out to be exactly the same as they were for the surface as a subspace of the interior geometry. So you should obtain exactly these same results. And that shows that the extrinsic curvature on the interior and exterior of the surface match, which shows that the two geometries, interior and exterior, match together smoothly.